Hello everyone, my name is Isha Deshmukh and I am a third year engineering student studying in PES Modern College of Engineering. This is a presentation video for the internship Embedded Systems internship under Emertxe Information Technologies. The project that I completed under the internship is Car Black Box. Moving ahead, these are all the contents that are going to be covered in this presentation video. This is basically an overview of the internship experience I had under Emertxe. So the first is the C module. This covered the basics of C language which were required as a prerequisite for the making of the project. So the different concepts that I learned were data types, different type of data types, integral and floating. Integral include char and int, floating had float and double, conditional constructs, that is if, else, block and switch for single iteration, and the loopings for multiple iteration. Then jump statements included break and continue. Then different kind of operators, arithmetic, relational, logical and bitwise. Then we learnt about the arrays data structure and the concept of pointers, referencing and dereferencing variables. Moving along, the further concepts were functions, recursion, that is calling a function inside itself, string. In string we learnt different built-in functions, and one of the functions that was used in our project is string compare, in which two strings are passed and it returns and it compares the two strings lexicographically. Then we learned about storage classes, extern, static local, static global. Extern keyword is basically used when we want to use a variable outside a file, inside a different file. Static means that the variable can be initialized only once. Static local is basically limited to the scope of the function it is declared inside, and static global can be used throughout the program. And then the header files, which include the C declarations and the macro definitions, and these header files can be included in your project using the hashtag include keyword. Then moving along, the second concept is embedded systems, or the second module was embedded systems. So what is an embedded system? Any combination of hardware and software which is intended to do a specific task can be called as an embedded system. So we have standalone we have different types of embedded systems. The first one is standalone, so it does not require any host to basically produce the output. Then real-time embedded systems are supposed to produce the output promptly or in the given time. Networked require either wired or wireless connection in order to communicate with web servers to produce their output. And mobile embedded systems are compact and portable embedded systems like cell phones. Then the third one is the project, that is the Car Black Box. The different tools that are going to be used in this project are the IDE, the Integrated Development Environment, is MPLAB XIDE. The compiler is XE8. The microcontroller that we are going to use is PIC16F877A, and the stimulator is PIXINLab. Moving along, now I am going to explain the different peripherals or the hardware that is required for building of the project. The first one is the CLCD. It stands for Character Liquid Crystal Display. We are using the 8-bit board and it is 16:2. That means there are total 2 lines, and on each line 16 characters could be displayed. And it has a 4-bit and an 8-bit mode. In the project we are using 8-bit mode. That means it has 8 input lines, and at one time one entire character can be displayed. Then the multiplexing is with port D. It has 2 modes, instruction mode and data mode, represented by binary 0 and 1 respectively. The RS, that is register select pin, is given this value to decide as to whether the instruction or the data register is to be selected. In the program, I have written 2 functions, clcd_print and clcd_putch. These are used either to display an entire string of characters or a single character. So the parameters are the data we want to display and the address at which we want to display this data on the CLCD. Then we are having 6 switches. So these 6 switches are multiplexed with port B, and these 6 switches are from RB0 to RB5. So we have level and edge triggering, and in this project we are going to use edge triggering. And we have a all release state and input line 0x3f, which I would be explaining in the below diagram mentioned. So as we can see, port B, there are total 8 pins from RB7 to RB0, but the switches we are using is from RB0 to RB5. So the input line we have chosen is 0x3f. So because we don't want to know the state of RB7 and RB6, we are going to add 0x3f so that we will get only the states of pins RB5 to RB0. And when none of these switches or pins are pressed, it is the all release state, and that all release state is equal to the input line, which is 0x3f. So that is why we have used this combination, and this is how whenever any pin will be pressed, by ANDing it with 0x3f, we will get to know which switch or pin is pressed. Moving along, next is the potentiometer. As we can see in the diagram, these are the symbols of the potentiometer in the Pixin lab. It is used to control the speed of the car. So basically the little circle inside the larger circle can be moved by the user, and then accordingly speed will be changed. So it uses analog to digital conversion. So in ADC, the output is a 10-bit binary number. It is stored in two registers, address high and address low. So we are using write justified storing for storing the 10-bit binary number. So because it is a 10-bit binary number, the output is in the range 0 to 1024, but the speed range that we are using here is 0 to 99. So that is why whenever we will get the output range, we are going to divide it by 10 so as to convert the output range into our speed range. So this is the use of potentiometer. Moving along, we have the EEPROM memory. It stands for electrically erasable programmable read-only memory, and it is a type of non-volatile memory. So it has two inbuilt functions, that is EEPROM write, in which we pass the address where we want to write and the value we want to write, and EEPROM read, and we pass the address from where we want to read the value. So this memory we are using for storing the password, the first 4 addresses for storing password, and the remaining addresses for storing the car events, which are basically the time, the event and the speed. Moving along is the microcontroller. As mentioned earlier, we are using PIC16F877A. It has got 5 ports, A, B, C, D, E respectively, and 3 timers. The input channels are 8, and then port A has 6 pins, port B, C, D have 8 pins, and E has 3 pins respectively. And we can see the diagram with all the namings of the microcontroller. Moving along, these are all the 3 timers, that is timer 0, 1 and 2 that are basically present in the microcontroller. We'll be using one of these timers, which I'll explain in the following slides. Now talking about what is interrupt and ISR. So basically what happens whenever an interrupt occurs. So whichever instruction the microcontroller is executing, it completes the execution of that instruction, and the next address of the instruction is stored in the program stack, and then the program control goes to service the interrupt service routine, and it also disables all the global interrupt enable. Now in the interrupt service routine, it is basically a piece of code that the microcontroller should execute in order to service the interrupt that has occurred. So what all things the ISR should do? It should clear the interrupt flag as the interrupt is getting serviced. Then it should save the register contents that may be affected by the code in the ISR, and it should be terminated with the instruction that is return from interrupt enable. And then after returning, the execution begins from the next statement which was supposed to be executed. Now we are having calculations for interrupt. So basically this is used for calculating like after how many seconds or after how much delay you want the interrupt to occur. So for example, the required time after which I want interrupt to occur is 0.5 seconds. The total ticks are 250, and the frequency of the oscillator is given to us. So quantum is calculated as 4 divided by frequency of oscillator. Quantum is the time required for one tick to execute, and the prescaler we are using here is 1:16. So the formula of count, that is after how much count should the interrupt occur, is equal to the required time divided by total ticks into quantum into scale, which gives us 1250 seconds. So after we get this value in the interrupt service routine of that timer, we will increment the count, saying that whenever the count is equal to the given value, that is 1250, we will service the interrupt, that is perform whatever piece of code or routine you want to perform, and after that we will set the value of count to 0 again, and then the timer would begin all over, would start all over again, and whenever that much delay of 1250 seconds would be elapsed, again this interrupt would be serviced. So this is the calculations for the interrupt. Moving along, the last peripheral is RTC, which is real time clock. So it keeps an updated track of time, and this information can be used by the microcontroller, usually over some serial communication, for any time dependent functionality it has to perform. So for this communication between RTC and the microcontroller, we are using I2C protocol, which is inter-integrated circuit. So it is a synchronous communication, it is half duplex, and it is multiple master, multiple slave. So because of multi-master, multi-slave, there is collision bound to happen. So that is why it has got collision detection. It is a two-line interface. It has a data line and a clock line, and it is wired AND. That means in the data line, if any of the devices becomes 0, all the other devices will also become 0. Moving along, we are talking about the I2C. So how exactly communication happens? So now whenever the master wants to communicate with a specific device, it sends the unique address of that specific device on the data line, and then basically whichever device for which it is intended will receive that address and send an acknowledgement back. That is how the communication would begin. So now condition for communication is whenever the clock line is high and the data line is from high to low, it indicates start of communication, and whenever the data line is from low to high, it indicates end of communication. And for data validity, whenever my clock line is low, that means on the data line write operation can be performed, and whenever clock line is high, on the data line read operation can be performed. Next, I am having multiplexing. So the clock line is multiplexed with R3 pin and data line with R4 pin. So now talking about the registers of I2C, we have SSP CON1 and CON2, which are the control registers. They are readable and writable. We have status register, shift register, buffer register, and address register. So now if my microcontroller is going to act as a slave, then the address register stores the address of the microcontroller. But if my microcontroller is going to act as the master, then the address register lower 7 bits is going to store the baud rate value. So in our program, the microcontroller is the master slave and the R2C is the slave register. So now talking about the receive and transmission operation. In receive operation, the shift register receives 1 byte, and after that it shifts it to the buffer, and from the buffer it is given to the receiver. In transmission, the user loads data to the buffer shifts it to the shift register, and from the shift register it goes to the receiver. So this is regarding the multiplexing of the I2C protocol between the microcontroller and the RTC, real-time clock. Now I am having is the project layout, that is the walkthrough of the working of the project. So this I would like to show the live demonstration. So this is the MPLab XID in which I have written my program. So here I am going to build my program now. So we can see the build is successful and loading is completed. So now inside the Pixel lab, I am going to go to file and load the hex file. So here car black box project, I am going to load it. So now as we can see, this is the dashboard, it is the LCD. So initially we have time, event and speed. So initially whenever you load the file, the event is on, and speed is wherever the potentiometer symbol is pointing. So now if I try to move it, we can see that the speed is changing. So now using the RB0 pin, which is basically switch 1, if I click it, the event will change to collision event. Using RB1, RB2, I can change the event to between the gears. So now it is gear neutral, gear reverse, gear 1, 2, 3, so on. And using RB2, I can come in the backward direction. I'll have gear 2, gear 1, gear reverse and gear neutral. So now RB3 pin or RB4 pin are used for entering the password. So whenever I click these pins, enter password screen would appear. And if I am not doing anything for more than 5 seconds, then it will automatically go back to the dashboard, as we can see. So now here the RB3 pin and RB4 pin are basically in our program, we indicate them as switch 4 and switch 5. So RB3 is switch 4 and RB4 is switch 5. So now switch 4 is used to enter the character 4, and switch 5 is used to enter the character 2, and the password that we have set is 2424. So now supposedly I go to the enter screen and I am entering 4444 and 4, which is the wrong password. So I get wrong password, 2 attempt remain, and then it again comes back to the dashboard screen, again comes back to the password screen. So I total have 3 attempts. So if I again enter the wrong password, So I am going to get wrong password, 1 attempt remaining. After again 5 seconds it come back to the enter password. So again if I am entering the wrong password, then I get a message, you are blocked, wait for 58 seconds. Wait for 60 seconds, and you can see that the seconds are reducing. So here the concept used is basically we're using timer 2, and we have made changes in the interrupt service routine, where we have written that whenever like the attempts have been 3, then we are going to block the user for 60 seconds. So now we'll have to wait for 60 seconds, and after that we'll again be transferred to the enter password screen. So in this, either you can use a interrupt service routine of timer 2 as we have used, or you can also make use of the time from RTC, that is the real time clock, and alter it to provide a message like this. So now after 1 second we are back to enter password. So now I am going to use the correct password, that is 2424. So now as it was the correct password, I get the menu screen. So here asterisk symbol is used to tell us that you can select whatever is written in front of that asterisk symbol. Again using RB3 and RB4 I can scroll. So I have clear log, change password, going up, clear log and view log. So now if I have to select view log and asterisk symbol is in front of it, I am going to use the RB5 pin. So here I can view the log in the format, the time, then the serial number, the event and the speed. So again RB3, RB4 to scroll. I have event log 1, log 2, 3, 4 and then coming up, so on. So from going to the menu screen back, I am going to use RB5 again. So now if I have to clear logs, I'll use RB5. And I get a message, logs cleared successfully. After 5 seconds then I am taken back to the menu screen. After clearing logs, if I want to see the view log, I get no logs because we just have cleared the logs. So now if I have to change password now, so I'll go over here and I'll click RB5, enter new password. Again using RB3 I'm going to enter the password 444 and 4. Here I'm having re-enter new password. So now using RB4 I am entering wrong password, 222 and 2. So I am getting password change failed, and then I'll be taken back to the menu screen again. And if I use the correct password now, in change password I am entering 4444. In re-enter I am entering 444 and 4. Again I get password changed successfully, and I come back to the view log screen. So this is basically the overview of the live demonstration of the project, which is known as the car black box. Coming back to the presentation, in conclusion, I'd like to say in this duration of this internship, I got to learn about embedded systems and various peripherals that exist. I have successfully implemented the car black box project. In future, I would use this knowledge in developing more different projects. Now this brings me to the end of my presentation. I would like to thank Emertxe Information Technologies for providing me with this opportunity. Thank you.